Okay, great. It's time to get started. And I'd like to begin by welcoming you all to our webinar entitled Regulatory, Operational and Technical Aspects of Testing for Enterococci in Drinking Water. My name's Andy and I will be your moderator for today. Just before we get started though, I'd like to quickly run through just a couple of housekeeping items. Firstly, you can all access the chat box at the lower right of your screens. Please use the chat feature if you want to send a message to everybody. We very much welcome questions from you all today. If you do have one, can you please type it in the questions panel rather than the chat panel? That will then enable us to manage the questions more efficiently. And if we don't get to answer everything during today's session, I do promise to follow up with you directly afterwards. And finally, a PDF of all the presentations today is available to download at any time. To do that, move your cursor over the screen for a moment until a cloud icon appears in the upper right of the window, and just click on that icon to be able to download the file. Also worth saying that a recording of the presentations will also be sent out to everyone after the end of our session today. Okay, let's go ahead and get started. Our first presenter today is Kristin Majeska, and she's going to talk about the new EU Drinking Water Directive and specifically the updates to microbiological testing requirements. Kristin is Director of Global Government Affairs and Market Development for the IDEXX Water business. She is an expert member of the ISO Water Quality Microbiological Methods Subcommittee and also Vice Chair of the Technical Advisory Group for ANSI, which represents the United States in ISO discussions. Kristin is also Chair of the Association of Water Technologies Cooling Subcommittee, and she has published numerous articles in industry journals and authored several book chapters. She earned an MBA at the Stanford Graduate School of Business. So it's my pleasure to hand you over to Kristin.
Thank you, Andy. So today I'll be talking about the recent update to the Drinking Water Directive for European Union countries. The Drinking Water Directive covers the quality that must be maintained for all distribution system water, which ultimately reaches the tap and could be used for drinking, cooking, etc. The goal, of course, is to protect the public from illness and even death, which can be caused by contaminated water. This directive is mandatory. It must be followed by all 27 member states. And note here that member state is just another way of saying a country which belongs to the European Union. And I'll be using both terms interchangeably throughout the presentation. Now, it's been more than 20 years since the previous version of the Drinking Water Directive was published. This latest version was adopted in December of 2020 after making its way through the European Parliament, the Council of 16, and many rounds of negotiation. The directive was then published in January of 2021. And I'd like to note that it is available on the European Union website, and it's available in every language of each member state, in case you'd like to take a look at the full document. The clock then started ticking on that same date of January 12th, 2021. Each member state has only 2 years to transpose the directive. That means to incorporate what the directive says into its own regulations or legislation. That may mean updating existing rules or adding new legislation. In some countries, we've looked at this, and it may be up to a dozen different laws that need to be updated or added. Now, it's important to note that any member country has the option to implement this directive with the specific requirements or their own requirements, as long as they are more stringent than what the directive requires. This directive is just a minimum. Now, the transposition process typically has a public consultation step, so do look for the opportunity to contribute your expertise and input directly. You may be able to do this as an individual stakeholder or through an association to which you might belong. Today, if with now June, I would note we're only 7 months away from the date, January 12th, 2023, that each country's national legislation not only needs to be in place, but it needs to start taking effect. So that's when additional testing that will be required is going to start to be needed to be done. So the directive has a number of significant changes. I've chosen to highlight just 3 of them, which are particularly relevant for water system operators and laboratories. The first is testing for intestinal enterococci, which is essentially just another way of saying enterococci. Now, this type of testing is already required in the existing directive, but in the new directive we're talking about today, enterococci has a new status. Essentially, it becomes what is called a core parameter. It means it's on par with E. coli, with a 1-to-1 testing ratio. There are a few EU countries that do already have this 1-to-1 E. coli enterococci relationship today, but for many of the member states, this is something new. A second significant change is a brand new requirement that Legionella testing must be done in domestic water systems. You can think about this as building water systems in priority buildings. Now, in contrast to the enterococci provision, however, this new directive requirement leaves lots of flexibility for the individual member states to decide what kind of testing should be done with what frequency and to define what buildings specifically qualify as priority buildings. Finally, utilities will need to implement system-wide water safety plans. Now, this is quite a significant endeavor. So the deadline, it's worth noting, for this particular requirement is for meeting the requirement by December 2026. So in terms of microbiology, the new directive specifies the minimum number of times you must test for 2 of the parameters that we'll talk about today. These are the core parameters. E. coli, as many of you on this call, I imagine, are doing today, and intestinal enterococci. The number of tests required will vary by the size of the system. The directive also requires testing for 5 other microbiological parameters, but the frequency required is allowed to vary based on the specific risk of the situation and of the system. Now, these non-core parameters are Legionella, colony count at 22 degrees, total coliforms, Clostridium perfringens, and somatic coliphage. So again, what's different about a core parameter? What you'll see when your country does its transposition into its national regulation or legislation is that for every E. coli test that is run in a drinking water distribution system, an intestinal enterococci test will need to be run as well. That's at the minimum. There may be more. And as you can see, the acceptable limits per the directive are also the same for both of these parameters. No detection above 0 per 100 milliliters, measured by number. That could be CFU or NPN. And here, very important, unlike some of these risk-based parameters, the water operator does not have the option to reduce the testing frequency based on a risk assessment or any other criteria for that matter. So what that means in conclusion is that for most EU countries, starting next January 2023, significantly more enterococci tests will need to be run. whether they're run by private laboratories or by the water operators themselves. And with that, I'll turn this back over to Andy, who will introduce our next speaker, who will provide some really valuable insights into just why more frequent enterococci testing in distribution water is valuable, and most importantly, how this requirement will contribute to public health. Thank you.
Thank you very much, Kristen. And again, please, if you have questions for Kristen, please remember to put them in the questions tab rather than the chat tab, and we will endeavour to answer them at the end of the presentation. So as Kristen said, it now gives me great pleasure to introduce you to Dr. Colin Fricker, who's going to discuss why drinking water is tested for the presence of Enterococci. Colin is Adjunct Professor of Environmental Studies at Queen's University, Kingston, Ontario, and has a long and distinguished career involved in water microbiology. He has published more than 90 peer-reviewed papers, edited 5 books, and presented over 200 papers at international conferences. Colin is also a consultant to many water utilities, some as far away as New Zealand, where he is on call to troubleshoot and give advice at a moment's notice. Welcome, Colin.
Thank you, Andy. I'd like to start by putting this a little bit into perspective, which means really, why should we be concerned about further testing
Yeah, thank you, everyone. It sounds like we've lost the sound for Colin. We will, if you bear with us, we'll do our best to get him back.
Is that back?
Yes, you are, Colin, thankfully.
My apologies, I'm not sure what happened there, so I'll start again from the beginning. The Havelock North report investigating the outbreak of waterborne disease in New Zealand in 2016 stated that somewhere between 1 in 50 and 1 in 250 of New Zealand's residents contracted waterborne disease during each year. So while we don't see particularly large outbreaks of disease often, it's well known that there's a considerable amount of sporadic disease. And for this reason, really we should be looking for whatever else we can do to try and detect problems associated with consumption of municipal water. So I'm going to start by talking a little bit about indicators, and I apologize if this is all things that you know, but it puts my presentation into some context. So ideally, indicators should be present whenever pathogens are present, be present only when the pathogens are of imminent danger of causing disease, which means they shouldn't really be growing in the water system. They should occur in much greater numbers than the pathogens. And this fourth one here, be more resistant to disinfectants and to the aqueous environment than the pathogens themselves. Also, they should be easily cultivable on simple media and yield characteristic and simple reactions. So in other words, there should be a lot of them, they should be there when pathogens are there, and they should be easy to detect. So when we look at the 2 indicators that are required now by the directive, E. coli and Enterococci, and look at some of their characteristics, We can see that the numbers of E. coli are in general higher than numbers of enterococci in feces and sewage, usually in the order of 2 to 3 orders of magnitude. However, their resistance to disinfection is lower. They survive for shorter periods in the aqueous environment. They transport through soil into groundwater more slowly or not at all, and they have a lower resistance to UV light. So what are enterococci? So the genus Enterococcus was first proposed in 1903 and consisted of just 2 species, Enterococcus faecalis and Enterococcus faecium, which are the two most numerous in human feces, typically. And subsequently, these were classed as Lancefield group D streptococci, which the Lancefield grouping is based on antigens on the surface of the streptococci. And then Enterococcus was revived as a genus in 1984 by workers in Germany and the UK, and new species were added. And since that time, taxonomy has continued to evolve and continues to evolve, and now includes at least 36 species, which are broadly clustered into 5 groups. So you've heard the terms already, Enterococcus and intestinal enterococci, and many of you will also have heard the term fecal streptococci. These names are largely synonymous, and certainly Enterococcus and intestinal enterococci can be used interchangeably. And all of the species described to date, or at least at the beginning of this year, all the species that have been described by the beginning of this year had been detected either in human or animal fecal material or in wastewater. And consequently, we conclude that there are no species that are entirely, exclusively environmental in origin. When we're trying to culture these organisms, most procedures are based upon detection of beta-D glucosidase, or maybe known as esculinase. And the detection is either chromogenic or fluorogenic. And selective agents that are used are azide and various antibiotics, and usually in combination with elevated temperature to act as further inhibitors to non-target organisms. There are reports, however, that the use of azide may impede the recovery of chlorine-stressed enterococci, and I'll show you a little data on that subject, and you'll also hear more of it later in this presentation. So here is some data on recovery of chlorine-stressed enterococci using Slanetz and Bartley medium, which is the traditional medium for fecal streptococci and is used in a wide number of laboratories for enterococcal testing, and 2 commercially available enterococcal tests. And what we can see is that in terms of the Slanetz and Bartley medium, when the azide concentration is reduced from the typical level that's used in culture media of 40 milligrams per liter, when it's reduced, the number of isolates that were detected in this study increased dramatically. And so when there was only 10 milligrams per liter of azide there, the number of confirmed isolates approached an increase of 80% over what was detected with 40 milligrams. And you can see also that when those Slanetz and Bartley plates were incubated, it extended incubation to 5 days, then more isolates were obtained. And this indicates that the azide level is inhibiting the growth of the organisms sufficiently to slow them down, and they take longer to form colonies on the solid media. You can see also that Enterococci, which is a liquid glucosidase-based method, recovered almost the same number of Enterococci as the Senetz-and-Bartley with reduced azide, but the confirmation rate was much, much higher. And the issue with using a Senetz-and-Bartley base with only 10 milligrams per liter of azide is that many more organisms other than the Enterococci will form colonies, which subsequently don't confirm. To summarize the culture methods, all culture methods rely on the detection of glucosidase activity, either for primary isolation or for confirmation. And Senetz-and-Bartley, the most widely used medium, was developed over 70 years ago. And there have been a large number of new media described since that time, although very few have been adequately validated. And I would suggest that one of the reasons that there's not been a huge interest in some of these new media is that Senetz-and-Bartley appears to perform very well, in that when you have colonies on that medium, they typically confirm to be Enterococci, but as the data that I just presented shows that they also are missing a significant number of organisms when there's been chlorine injury. It does appear, however, that no single method is ideal for all species, and it's quite clear that we need more detailed validation studies of some of the new media that are available. So when is it useful to monitor for Enterococci? Well, certainly for groundwater sources. They survive better than other indicators outside of their natural habitats, and the morphometrics and surface characteristics of the Enterococci facilitate their fate and transport through soil. And there have been several studies showing that Enterococci can occur in groundwater in the absence of traditional indicators such as coliforms. And furthermore, fate and transport studies often more closely follow those of viruses rather than coliforms. So there's some evidence that the fate and transport of Enterococci is similar to at least some of the viral pathogens that are waterborne. In distribution systems, Enterococci are very useful as indicators for ingress, and there have been studies in Sweden and other countries which have demonstrated an increase in gastrointestinal disease correlated with heavy rainfall events, and the illness was postulated to be associated with increased ingress into the system during these wet weather events. And there has been demonstrated a positive correlation between Enterococci and pathogens. And the longer survival and higher chlorine resistance of Enterococci makes them a suitable indicator in these circumstances. And I would point out that detection of total coliforms and Enterococci together is a strong marker for fecal contamination. During water quality events, I've been involved in, an awful lot of investigations into water quality events, and one of my recommendations for monitoring is always to use Enterococci in these situations, both during and after. The residual disinfection is often increased during and after events in order to try and clear any pathogens that may be lingering in the system. And so that higher chlorine resistance of Enterococci makes them extremely useful for clearance monitoring. That's monitoring that tells you that there's no likelihood of pathogens lingering in the distribution system. So there are several situations where Enterococcus monitoring provides additional information. They certainly give a better understanding of treatment plant performance than the traditional indicators of fecal contamination, E. coli. Certainly a better understanding of groundwater contamination, and there's lots of evidence showing that. They're particularly useful for differentiating between presence of coliforms in distribution systems due to biofilm or ingress. And although there have been some studies showing that Enterococci can be incorporated into certain biofilms, they don't seem to be incorporated into water network biofilms to any great extent. And so using this additional marker of Enterococcus monitoring, it's my belief that certainly a significant amount of sporadic waterborne disease could be reduced. So is this just my belief, or does anybody else actually believe that Enterococcus monitoring is of any value? Well, there have been, as I've said, many studies showing the presence of Enterococci in untreated groundwater in the absence of other fecal indicators, which is certainly, to my mind, makes monitoring of groundwater sources for Enterococci a very sensible thing to do. The World Health Organization suggests that Enterococcus monitoring should be implemented for when determining the sanitary quality of new and repaired mains. And again, that's something that I've recommended on a number of occasions to water utilities around the world, and have seen a number of occasions where we've detected Enterococci in both new and repaired mains in the absence of coliforms or E. coli. The European Commission clearly believes that there's value in monitoring for Enterococci, and hence the change to the directive. And they've demonstrated that monitoring for Enterococci would detect water quality issues in the absence of E. coli in some instances. And a very interesting fact that if you dig through the annual reports of the UK and Ireland's drinking water data, they've shown that Enterococci can occur relatively more frequently in water at the point of consumption. That means that the percentage number of samples which contained Enterococci was higher than the percentage number of samples that contained E. coli in some instances. So in conclusion then, Enterococcus monitoring is a useful supplementary tool for detecting water quality events. It's not there to replace E. coli, but it's there as an addition, and it's certainly, all the indications are that by monitoring for both, then that's a much more conservative approach, and you're more likely to detect contamination events or water quality events in a distribution system particularly. There's no doubt that Enterococcus is a superior indicator of groundwater quality over E. coli and coliforms. And so, as I've said, I believe that Enterococcus monitoring should be mandatory for groundwater sources. Monitoring for cleanliness of new and repaired mains, as I've said, the World Health Organization recommends that, and I would certainly strongly support that view. And similarly, for when monitoring to assess treatment plant efficacy, Enterococcus is one of the most useful indicators that we have. And finally, there's good evidence that analysis for Enterococci is useful for differentiating between biofilm and ingress-derived coliforms in distribution networks. And at that point, I'll end and hand you back to Andy.
Thank you, Colin. And I just want to apologise to everyone. We did have experienced some quite bad sound quality there, and we can only apologise. Maybe we'll be able to fix it in the recording of the presentations that we're going to send out subsequent to the event. So our final presentation is from Dr. Brett Bruin, entitled New Horizons in Enterococci Testing and Recent Results from Real-World Trials. Brett is our EMEA Technical Manager here at the IDEXX Water Division. He's been active in the field of water microbiology for over 2 decades. His initial interest in the molecular biology of nitrogen fixation switched to waterborne disease following the completion of his doctorate. Brett has over 20 years of practical experience in product development and the analysis of water for the presence of fecal indicator organisms and waterborne pathogens. He has worked closely with laboratories, experts, and regulatory bodies around the world, developing new technologies, training analysts, and establishing best practice in order to optimize often complex technical procedures and generate robust methodologies. Brett, welcome.
Thanks, Andy. Good morning, afternoon, evening, everyone, depending on where you are in the world. And thank you for joining us for this presentation. Today, I'd like to share some comparative technical data with you that's been generated using the Enterolert DW method and the reference method ISO 7899-2 for the detection of Enterococci. And the reason I'd like to go through these trials that have been performed over the last 12 years is because I've been involved in all of them on a technical level, and I've worked with many countries and many great laboratories in seeing these trials through. I'll begin by sharing some brief details of the trial procedures themselves that we use when we're comparing two methodologies. And following on from that, I'm going to share some details of the individuals trials performed over the last 12 years or so, along with a summary of the results obtained during each trial. So as Colin previously said, we do find Enterococci in drinking water and often more frequently than E. coli. However, for a trial purpose, for a statistical analysis, the numbers aren't so great. Therefore, we have to generate artificially contaminated samples. And so during each trial, we've used primary settled sewage effluent as a source of Enterococci. Obviously, in effluent, the organisms are not typically injured. So we take them through a chlorination procedure in order to mimic the water treatment process. We then take potable waters from various geographical locations and we inoculate those water samples with both chlorinated effluent and unchlorinated effluent to generate our water samples. The whole process is pretty labor intensive, so we're always grateful when labs are willing to work with us. On day one, the effluent is screened, so we know the levels, the concentration of Enterococci in the effluent sample. Day two, we'll take them through a chlorine injury procedure, and then they're screened again so we can determine the log reduction in Enterococci in that chlorinated sample. Day three, we take our potable water samples, we work out the volumes of the chlorinated and unchlorinated material we need to generate approximately 50 to 80 CFU per 100 ml sample, and then we inoculate those samples. And we process them using both the Enterolert DW method and the reference method. And finally, it's just data collection. Day four, we collect our results for Enterolert DW, and then a day later, we collect the results for the reference method. So the first trial I'd like to talk about was the very first trial for Enterolert DW back in 2010. And this was a pan-European trial. It involved 8 laboratories in 7 countries. So laboratories in Italy, Belgium, Spain, Germany, France, Finland, and 2 in the United Kingdom took part in this trial. Each laboratory performed the trial over a 2-week period, generating approximately 30 data pairs per week. So this is just a very brief summary of the data generated during that trial. And if you look at the scatter plots, you can see that the performance of Enterolert DW and the reference method ISO 7899-2 for unchlorinated samples appears to be quite similar there's quite a nice distribution of the data, but it's fairly even across the line of equivalence. However, for the chlorinated samples, the performance of Enterolert DW appears to be superior. The method appears more sensitive and is detecting more Enterococci than the reference method, and you can see that a lot of the data is skewed to the right of the line of equivalence. Subsequently, when we analyze the data using statistical methods outlined in ISO 17994, we can see that for both sample types, the Enterolert DW was statistically determined to be more sensitive than the reference method. And that's quite interesting, really. The greater sensitivity of Enterolert DW when chlorine injured samples are used may be related to some of the comments that Professor Fricker just made, who suggested that the high concentration of sodium azide used in the Slanitz and Bartley medium may adversely affect sensitivity, certainly in some cases. Okay. The second trial that I would like to talk about is actually a method validation. And this was conducted by an expert laboratory in France under the guidance of the AFNOR committee, so the French normalization committee. This method validation is performed in two parts. So firstly, there is an intra-laboratory study that's performed within the expert lab. And there they define various categorical performance characteristics, things such as relative accuracy, linearity, limit of detection and quantification, inclusivity, so that's looking for your desired target, and exclusivity, that's your non-targets. And these define the performance of the Enterolert DW method itself. Subsequent to that, there is an inter-laboratory study where typically a minimum of 12 labs will participate. The expert laboratory generates the samples and sends those to all participants who process the samples and report their results. So during the inter-laboratory study, all the criteria that we've detailed were assessed and they were determined to meet acceptable levels. And then during the inter-laboratory study itself, and you can see a couple of scattered plots there for the data produced by the 12 participating laboratories. The comparative performance of Enterolert DW was determined to be acceptable and equivalent to the reference method. And then based upon these findings, which were presented to the AFNOR committee, they granted Enterolert DW certification as a validated method, and that occurred back in 2013. Following on from that, a number of countries decided to do their own trials. And so the third trial I'm going to talk about is a one lab verification, which was performed in Hungary back in 2017. And this is fairly typical route that people will take. The health department will commission a study to validate the method themselves, generate some data, analyze that data. The trial followed the same format as those previously done, again using uninjured effluent and chlorine injured effluent, and we performed the training with that laboratory in order to carry that out. The statistical analysis of the data performed, again, according to ISO 17994, that's the standard for comparing microbiological methods, particularly with water, indicated that for uninjured samples, the methods were not different. But again, with the chlorine injured samples, the Enterolert DW method was determined to be more sensitive and detected more Enterococci. And again, based upon these findings, the health department authorized the use of Enterolert DW as an alternative method. And again, it's interesting just to note that again, with the chlorine injured organisms, Enterolert DW appears to be more sensitive. And that comes back to the comments that Colin made earlier. In 2018, there was a comparative trial performed in Poland with the objective, again, of having enterolert DW accepted as an alternative method. In this case, the regulatory body in Poland didn't think that a one lab verification was sufficient, and so they chose to perform a multi-laboratory study. Again, we were involved in training all of those labs. However, the trial itself was all performed independently in the 5 labs around Poland. We are still following the same format, so we're taking sewage effluent, performing a chlorine injury, inoculating our drinking water samples, processing those samples, and then performing the analysis according to ISO requirements. Again, if we look at the scatter plots, the performance of enterolert DW and the reference method appears to be quite similar, just eyeballing the data there. And this is for both uninjured and chlorine injured water sample types. However, when we analyze the data according to ISO 17994, we can see in this case for uninjured samples, the enterolert DW method was determined to be more sensitive. But for the chlorine injured samples, the methods were found to be equivalent, i.e. not different. The trial portfolio, data portfolio has been submitted to the regulator, and the output or the outcome of this trial is still pending. But the statistical analysis we performed is very favorable in terms of the enterolert DW method. Moving on to 2020, I'd like to discuss a lab trial that was performed in Spain. And this particular trial is probably one that I'm most proud of in my tenure at IDEXX. The reason for that is that it was probably the largest trial we ever undertook. It was involving 15 laboratories, all geographically located all over Spain. It was also very stringently controlled by a corporation called AEAS. I'm not going to try and pronounce that in Spanish, but AEAS basically guided us on how the trial should be performed, and we had to submit very stringent protocols which they would review and agree upon. The trial again involved 15 laboratories, and it's not possible to perform training for all of those individual laboratories, and so we took a slightly different path. We appointed 2 central expert laboratories who were trained to produce injured and uninjured chlorine effluent materials, which were sent out to all the participants. So this is following the model that AFNOR typically use with their validations. And all of this was done during the 2 years that we had with COVID. So again, I'm extremely proud of this trial. Hopefully there are some people on the call who were involved in this, and we're very grateful for them because it was a significant undertaking, a lot of effort over probably 12 to 18 months. These are the data that were produced by the reporter from AEAS. And looking at this particular scatter plot, you can see that the enterolert DW method and the reference method ISO 78992 were not equivalent. The enterolert DW method was more sensitive. And based upon these findings, enterolert DW has been written into the Royal Decree in Spain and is expected to be accepted in Spain as an alternative methodology. Finally, on to 2022 and a comparative study that is actually still ongoing in Portugal. This particular trial involved 3 participant laboratories. All of those were trained independently, but we had to still do this virtually. COVID was still in place, travel restrictions were still in place. So we did a lot of virtual training. That poses some challenges, but the 3 participant labs rose to the occasion and have been performing extremely well. Again, although this trial is still to be completed, we're still getting the final data in and still have to do some analysis. We have analysed the data from the first 2 participants, and I can share that with you today. And again, as you can see from looking at these scatter plots, the performance of Enterolert DW appears to be superior for both chlorinated and unchlorinated water sample types. A lot of the data is skewed to the right of the line of equivalence, and that is in favour of Enterolert DW. And again, analysis of the data according to ISO 17994 confirms that result. We are still waiting on the final data, which will be compiled with that that's already in existence, and that will be analysed once available, and we'll share that. So that's a brief look at the comparative data that's currently available for Enterolert DW and the reference method that's been previously discussed. If you do want to take a more in-depth look at the data and the statistical analysis, reports are available upon request, so please contact us and we'll share those with you. Thanks for your attention. I'll hand back to Andy.
Brett, thanks ever so much. And yeah, that concludes the official presentations from our 3 speakers today. Excellent insights, everybody. Thank you very much. And we have lots and lots of questions coming through. We've got about 10 to 12 minutes left that we can jump straight in. First one is a quick one. It was answered in the chat, but maybe worth reiterating to the whole audience. Colin, can you explain what ingress means? I think our friend in Poland, Joanna, asked that question.
Sure. Ingress is the entry of water from outside a distribution network back into that network containing soil, legal material, or just water. So either through leaks in the pipes or leaks in the roof of reservoirs.
Okay, thanks, Colin. We're still having a little bit of trouble with your microphone. So maybe the next question I'll direct to, this is an excellent one, I'm going to direct to Kristin. Why has this new EU water testing legislation come about? Have there been significant increases of harm to human life? Kristin.
That's actually a great question. So really, I think we're in a situation where the science has evolved over the last 20 years, so that researchers and public health officials, have a better understanding of how we can manage and improve water quality. And at the same time, as a society, I think we're really setting higher and higher standards for public health protection. So, as Dr. Fricker explained, kind of when we know what can be done better, there's an expectation that that should be put in place.
Excellent, thank you, Kristin. And while I've got you, another one for you. Have the levels of enterococci, similar question, have the levels of enterococci bacteria contamination increased across Europe or in specific countries?
Yeah, it's another interesting question. I can't speak to the specific enterococci levels, but I think what's important is that researchers, as again, Dr. Fricker kind of touched on this, have found that fecal contamination was occurring that wasn't being detected by E. coli analyses alone, but could be detected and then quickly responded to when they had a notification they could get because of enterococci testing. And also this finding that both E. coli and enterococci are together, if you look at them together, it's a particularly strong way to identify contamination that has to be addressed. So it's really the rather than the levels themselves, it's the function that finding this enterococci in the water provides for guidance for system operators and officials.
Excellent, thanks, Kristin. And I'm just going to give, rather than fire more questions to Colin, I'm going to give him a little bit more time to get his audio working again. And another question to you. Do all enterococci tests comply with the new directive or just select ones? I think that's quite a large question.
Yeah. So it really depends on the country. So the directive lists a reference method, excuse me, Slanets and Bartley, and a number of European countries also allow the use of Enteralert DW as an approved method. And a number of other countries are also in the process of adding Enteralert DW as an approved method for this purpose during their transposition process. Again, this is as they write up their own national regulation. And again, another reminder that as those public consultations go out, be on the lookout for them so that you can contribute your perspective. So a couple of countries where Enteralert DW is already included for compliance testing include Germany, Belgium, Hungary, Latvia, Norway, as well as our friends in the UK, who of course aren't technically covered by the directive. And if you've got a question about your country and kind of where they might be in this process, you can reach out to IDEXX Tech Support, and that email's on the screen, as is the phone number, or your local in-country IDEXX representative. And of course, Slanets and Bartley is also accepted for all of the member states.
Thanks, Christian. Right, we're going to try Colin again. Colin, someone has asked if Enterococci results need to be confirmed, or are presumptive results sufficient? Reference to the DW, the new directive.
Okay, I'll try and answer this, but I can see the sound quality is poor. So
not too bad.
Kristen has the answer actually, which I've jotted to her, so she could perhaps answer it so people can hear more clearly.
Yep. So I'll just be. Thank you. I'll channel you, Dr. Fricker. So whether you need to confirm depends on the method used for primary detection. What he said is that what the studies have shown is that results using Enteralert DW do not require confirmation. The results of studies using the EU reference method against Slanets and Bartley has a confirmation rate of around 85%. So that means about every 100 colonies detected on SMB, about 85 of those are Enterococci. So it's really dependent on the method. And Colin, if you'd like to elaborate any further.
No, that's good, I think.
Okay. I think in similar vein, another question that we would direct to Colin, but he's kindly sent a written answer. What are the best ways to treat drinking water that has high levels of Enterococci contamination? And Colin's response is, although Enterococci are more resistant to chlorine than E. coli and coliforms, disinfection with chlorine is still the most cost-effective and efficient process for drinking water. Typically, pre-treatment using coagulation and filtration, whether that's sand or membrane, would be used, which enhances the effectiveness of chlorine. Okay, questions flooding in. Brett, I wonder if you can answer this one. What is the incubation temperature for Enteralert drinking water and for the Slanets and Bartley method, please?
Yeah, thanks, Andy. So good question. The Enteralert DW method is incubated at 41 degrees C. And the reason for that is IDEXX found that it gave the best balance between having adequate sensitivity while still maintaining good selectivity. In contrast to that, the ISO 7899-2 reference method is incubated for 48 hours at between 34 and 38 degrees C. It's a little bit dependent on local guidelines you might be following. In the EU, I think it's 36 plus or minus 2. And then there's an additional confirmation step that's performed with the reference method at 44 degrees centigrade for between 2 and 4 hours. Again, that depends on local guidelines that you're following. Interesting point is that, the dual temperature, so incubating at that lower temperature, there's a lower selectivity there. And then when you increase to 44, you're increasing the selectivity of the methodology. And that dual temperature might result in some of the presumptive colonies not confirming as Enterococci, even though they may in fact be, particularly with some of the slower growers such as Enterococcus durans. I hope that answers.
Yeah, thanks, Brett. And while I've got you, a quick one from Sarah. Thank you for the presentation on your results. Could you please inform about more false positive numbers? She's saying the 2010 study had a 0.3% rate.
Yeah, I can comment on that. And again, in the full reports for each of the trials, that information is present. In addition, what we've done is we've taken the data from each and every trial and reinterpreted that data and created categorical characteristics for sensitivity, selectivity, specificity, false positives and negatives, and all of that information is in some technical summaries that again we'd be happy to share. Briefly commenting on the levels, they're always quite similar, typically less than 5% false positive rate. There aren't any real criteria for a maximum false positive rate in ISO 13843, but typically we would see less than 5%, which appears to be acceptable.
Excellent. I think we can just, there's one quick question that I'm going to squeeze in. Kristin, where can I get a copy of the directive in my language, please?
Yes, so that is on the EU website, and I believe that may already be in the chat, but if one of our technical team members can put in that link in the chat, if you'll click down, you'll see when you open the page, it has the title of the document, and underneath it's got the abbreviation for each country, and when you click on that, you'll see the whole directive in your language. And there I see it's in the chat. Thank you, Nancy.
Brilliant. Thank you very much. So I think that's probably all we've got time for questions. We have got a lot that came through that we were unable to answer, but we can assure you that we will be following up every single question directly with you after the webinar. And if you're watching this on demand and not live, you can send questions to the email address that's currently on the screen. That's EMEA tech support @idexx.com. So just as a reminder, before we close the session, if you want to download a PDF of today, click on the cloud icon in the upper right of your screen. And also after the session, you will receive an email with a link to the recording, and we will do our best to try and get Colin's section a bit easier to hear. So yes, thank you very much for sharing your time with us today. Thanks again to our expert speakers, Kristin, Colin and Brett, for sharing their expertise. And yeah, thank you. I hope you enjoy the rest of your day. Bye-bye.